Welcome everyone. This lecture is about asymptotes. So we are going to learn about asymptotes and different types of asymptotes in rational functions. First of all, to begin with, what is an asymptote? It is just a line, nothing but a simple line, a straight line. What kind of line? A line that a graph approaches but never touches. The definition of asymptote is a line that a graph approaches but never touches, in very simple language. Now, a line, logically speaking, can be either horizontal like this, or it could be vertical, or perhaps it's slant, or we call it oblique sometimes. So that means that we have three different types of asymptotes for a rational function. Of course, some may have one and not the other one, but generally speaking, rational functions can have either a vertical asymptote or horizontal asymptote or slant asymptote. Vertical asymptote, well, it's a vertical line that the graph, whatever it looks like, approaches but never touches it. So the distance between the line and the graph is like getting smaller and smaller as x approaches the x value of the vertical asymptote. Let's say this is x equals a, okay? So that's how it looks like. The graph becomes extremely close to the vertical asymptote, and the graph could either approach positive infinity or negative infinity at the bottom. Horizontal asymptote is a horizontal line, so a curve could approach this horizontal line from below or from above sometimes. But that's how the horizontal asymptote looks like. It's a horizontal line. The equation is y equals b in general, parallel to the x-axis, and the graph becomes extremely close to it. In case of slant asymptotes, well, the line is oblique, so the equation is clearly y equals mx plus b, needless to say, and the graph could approach this line from above or from below. So we have three different types of asymptotes. And these asymptotes happen in rational functions of the form f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot, 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 just like that. It continues up to a sub 2x squared plus a sub 1x plus a sub 0, which is nothing but a polynomial function in the numerator, a polynomial function of degree n. The denominator is another polynomial function, but this time of degree m. So we use b sub m times x to the one of m, and then bm minus 1 times x to the m minus 1, all the way up to b sub 1x plus b sub 0. So basically we have two polynomial functions in the numerator and the denominator, okay? Now, the question is, how do we find the equation of the vertical asymptote? Well, again, in very, very simple language, you have to set the denominator equal to 0, as the flowchart says. For example, if you have a function like this, you're going to set the denominator equal to 0. So we get x cubed minus 9x equals 0. From there, when you factor, you get factor x out, you get x squared minus 9, which is a difference of squares. So that's x minus 3 times x plus 3 equals 0. Now, when you set this denominator equal to 0, you get like three roots. So x equals 0 is one of them, x equals 3 is another one, x equals negative 3 is the other one. Now, these two, x equals negative 3 and x equals 3, are definitely equations of the vertical asymptote, okay? Now, you may say, why did I not count x equals 0? Because this is just an exception. X equals 0 is the root of the numerator as well. So this factor x right here not only exists in the denominator, but also in the numerator. So when we have cases like this, and we have a root of the denominator, which is also a root of the numerator, then in that case, at that point, let's say x equals 0 in this case, the function becomes undefined, because the top is 0, bottom is 0. Imagine if you set x equal to 0, you get 0 in the top, 0 in the bottom. What is 0 over 0? In calculus, we call it the indeterminate form. So that means that there is no particular value like positive 3 or negative 3, and we cannot say those are the vertical asymptotes. So in these exceptional cases, these are called holes. So we have a whole at x equals 0. So this function has two vertical asymptotes, but one whole at x equals 0. Now, this was just a coincidence. If the numerator was something else, let's say 2x minus 5, okay, or some other linear factor, in that case, the x in the denominator would not become a common factor with the numerator. So in that case, we would say x equals 0 is actually the third vertical asymptote of the function. But in this case, of course, x is common in the top and the bottom, and therefore we have a whole at x equals 0 and not a vertical asymptote. So this function has two vertical asymptotes and not three, that sometimes some students by mistake might think it has three. So the moral of the story is this: when you set the denominator equal to 0, you should not do this blindly. If there is no common factor in the denominator and numerator, sure, in that case, all the roots that you find in the denominator, 0, 3, negative 3, or even more, those are all equations of vertical asymptote. But if you have a common factor, then those are your wholes. In case of horizontal asymptote, how do we find horizontal asymptotes? Well, there are three scenarios out there. Either the degree of the top and the degree of the bottom are both the same, I mean n equals m. For example, you have quadratic function at the top, quadratic at the bottom, linear at the top, linear at the bottom, cubic at the top, cubic at the bottom. If those polynomials have the same degree, then in that case, y equals the ratio of the leading coefficients would be the equation of the horizontal asymptote. Let's say a sub n is like 5 and b sub m is like 2. So y equals 5 over 2 becomes the equation of the horizontal asymptote. Like in this example, the top and bottom are both linear. So n is equal to 1, m is also equal to 1. So n equals m, that means that y equals 4 over 2, okay, which means y equals 2, if I simplify, would become the equation of the horizontal asymptote for this function in this example. But not always the case is this case. Sometimes the top is like quadratic, bottom is cubic, for example. I mean, the degree of the numerator is less than the degree of the denominator. In other words, n is less than m. If that happens, then always 100% of times y equals 0, that is the x-axis, will be the equation of the horizontal asymptote for that particular function. So right now I can say that this function, if somebody draws the graph of it using technology or graphing calculators or whatever, then you're going to see that y equals 0, or actually the x-axis plays the role of the horizontal asymptote. So the third scenario is when the degree of the top is more than the degree of the bottom. For example, the top is cubic, bottom is linear, for instance. In these cases, you're going to immediately announce that there is no horizontal asymptote, period, okay? So right now, this function here, it's a rational function. The numerator is a cubic polynomial, the denominator is a linear polynomial, and without, hesitation, I'm going to announce no horizontal asymptote, okay? And the reason why I say so is because n is greater than m. But the thing is that when n is greater than m, and we say we don't have horizontal asymptote, there is a chance for the function to have another asymptote, which we call it slant or oblique asymptote. So we already know that we don't have horizontal asymptote. So this error comes out from this box, and it goes all the way to two other boxes. So when we say n is more than m, well, the top could be like cubic, bottom linear, like in this example. So that means that 3 is greater than 1. Or the top could be like 4, bottom 1. Top could be 5, bottom 1. Okay? But if the difference between them is 1, I mean the degree of the top is 1 more than the degree of the bottom. I repeat, if the degree of the numerator is 1 more than the degree of the denominator, in that case we do have a slant asymptote. So this one doesn't have, but this one does have, because the top is quadratic, bottom is linear. So 2 minus 1 is 1. So the degree of the top, which is 2, is 1 more than the degree of the bottom, which is 1. So this function for sure has a slant or oblique asymptote, okay? But this one didn't. Okay, and what happens if the difference between the degrees is like more than 1? Like n is not equal to m plus 1, but at the same time n is greater than m, just like in this example, 3 is greater than 1, and 3 is not equal to 1 plus 1. So in that case, we're going to announce no slant asymptote, bye-bye, done. So 5 times x to the 4 divided by x squared plus x minus 1. This one has no slant asymptote because the degree at the top is 4, the degree at the bottom is 2. And in fact, this function did not even have a horizontal asymptote, okay? But this case, when n is equal to n plus 1, we do have slant asymptote. And the last question is, okay, how do you find it? There is, again, a simple explanation here. It says use long division. But how? Well, you're going to divide the top by bottom using long division, or any method actually you want, and you're going to take the quotient, okay? The quotient will always be in the form of y equals mx plus b. It's going to be always linear. And y equals to that quotient will be the equation of the slant asymptote. Like, it can't be explained as simple as that. So you just perform a long division, and you write y equals whatever the quotient is. This is the fastest, easiest way of finding the slant asymptote. And I explained when do we have a slant asymptote and when we don't have slant asymptote. I explained that. So here, if I want to do it, so I'm going to quickly divide the numerator by the denominator. So I get x squared plus 2x. Now we subtract, we get 4x minus 1, and then plus 4, so 4x plus 8, when you subtract, you get negative 9. So remainder, we're not interested, but I got this quotient of x plus 4. Therefore, I'm going to announce y equals x plus 4 is the equation of the slant or oblique asymptote for this given function. That's how easy it is to find the slant asymptote. So I think with all these examples and with this nice flowchart, if you call it nice, which summarizes the whole story of asymptotes, it explains what an asymptote is, it explains different types of them, it gives you an idea of the shape, it talks about the functions that have asymptotes, and it clearly tells you how to find the vertical asymptote, how to find the slant asymptote, how to find the slant asymptote. And one more thing you have to notice is that whenever there is a horizontal asymptote, you cannot have slant asymptote at all. And whenever you have a slant asymptote, that with this arrow comes to this box, meaning that there is no horizontal asymptote in case of the existence of slant asymptote. So I forgot this arrow, I just noticed. So now this flowchart is really perfect. Okay, so I hope you understood how we find different asymptotes of rational functions. And now all you need to do is to do like so many questions and try to find the asymptotes, different asymptotes of different rational functions. Thank you for your attention.